In this video, we will discuss first application of De-Moivres theorem, which is we have to express cos n𝜽 and sin n𝜽 as finite sums of powers of trigonometric functions of theta, where n is a positive integer. We know that by De-Moivres theorem, we can write cos n𝜽 plus iota sin n𝜽 equal to cos theta plus iota sin theta raised to power n. It is given that n is a positive integer, and we can apply binomial theorem on these type of terms when power is positive integer. And the formula for binomial theorem is a plus b raised to power n equal to a raised to power n plus nc1 a raised to power n minus 1 b plus nc2 a raised to power n minus 2 b square plus up to so on, where nc1 can also be written as n1, and same is the case for all other terms written in the form of NCR, and NCR is equal to n factorial divided by n minus r factorial and r factorial. Now by De-Moivres theorem, we can write cos theta plus iota sin theta raised to power n as cos raised to power n theta plus nc1 cos raised to power n minus 1 theta into iota sin n theta plus nc2 cos raised to power n minus 2 theta into iota sin theta square plus nc3 cos raised to power n minus 3 theta into iota sin theta cube plus nc4 cos raised to power n minus 4 theta iota sin theta raised to power 4 plus nc5 cos raised to power n minus 5 theta into iota sin theta raised to power 5 plus up to so on plus nc n minus 1 cos theta into iota sin theta raised to power n minus 1 plus ncn into iota sin theta raised to power n. We can also write it as cos raised to power n theta plus writing iota in the start of this term, we get iota nc1 cos raised to power n minus 1 theta into sin theta. Iota square is equal to minus 1, so this term will be minus nc2 cos raised to power n minus 2 theta into sin square theta, and iota cube is equal to minus iota, so this term will be minus iota nc3 cos raised to power n minus 3 theta into sin cube theta plus iota raised to power 4 is equal to 1, so this term will be plus nc4 cos raised to power n minus 4 theta into sin raised to power 4 theta plus iota raised to power 5 is equal to iota, so this term will be iota nc5 cos raised to power n minus 5 theta sin raised to power 5 theta plus up to so on, plus we will write iota as iota raised to power n minus 1 into nc n minus 1 cos theta sine raised to power n minus 1 theta plus iota raised to power n into nc n sine n raised to power n theta. Let it be named as equation number 1. To further solve it, we will consider two cases, first when n is even and the second when n is odd. Consider the first case when n is even. Let us rewrite the equation number 1. If we carefully examine the equation number 1, we can see that when there is odd number at this place, there is iota with these terms, and when there is even number at this place, iota is not present with these terms. Since it is given that n is even number, so here this n is even. When n is even, then n minus 1 is an odd number. Since this n is even, so with this term there should not be iota present at this place, and since n minus 1 is odd, so there should be iota with this term, but it should be just iota, not iota raised to power n minus 1. So modify these two terms. We will firstly write iota raised to power n minus 1, and it can be rewritten as equal to iota into iota raised to power n minus 2. When we will combine this term, we will still get iota raised to power n minus 1, which can be written as iota into iota raised to power 2 raised to power n minus 2 by 2. When we will cancel out these two 2's, we will get the same term. So it is equal to iota, and iota square is equal to minus 1. So it will be minus 1 raised to power n minus 2. And to modify this term, we can write iota raised to power n equal to iota square raised to power n by 2. By cancelling out by these two 2's, we will get iota raised to power n. So these two terms are equal, which is equal to iota square is minus 1 and raised to power n by 2. Now by replacing these two values in place of iota raised to power n minus 1 and iota raised to power n, we get cos n theta plus iota sine n theta equal to cos raised to power n theta plus iota nc1 cos raised to power n minus 1 theta sine theta minus nc2 cos raised to power n minus 2 theta sine square theta minus iota nc3 cos raised to power n minus 3 theta sine cube theta plus nc4 cos raised to power n minus 4 theta sine raised to power 4 theta plus iota nc5 cos raised to power n minus 5 theta into sine raised to power 5 theta plus up to so on, plus iota minus 1 raised to power n minus 2 by 2 n cos theta sine raised to power n minus 1 theta. Here this n is calculated by the formula that I have written n for NCR in the start. NC n minus 1 is equal to n by that formula, plus minus 1 raised to power n by 2 sine raised to power n theta. And by the formula for NCR, NCn is equal to 1, so we have not mentioned it here. Now, by equating real and imaginary parts, we get cos n theta equal to cos raised to power n theta minus nc2 cos raised to power n minus 2 theta sine square theta plus nc4 cos raised to power n minus 4 theta sine raised to power 4 theta plus up to so on plus minus 1 raised to power n by 2 sine n theta, where sine n theta is equal to nc1 cos raised to power n minus 1 theta sine theta minus nc3 cos raised to power n minus 3 theta sine cube theta plus nc5 cos raised to power n minus 5 theta sine raised to power 5 theta plus up to so on plus minus 1 raised to power n minus 2 by 2 n cos theta into sine raised to power n minus 1 theta. So we will use these two formulas whenever we have to express cos n theta and sine n theta as the finite sums of powers of trigonometric functions of theta whenever n is an even positive integer. Now consider the case when n is an odd integer. So let us rewrite the equation number 1. In equation 1, we can see that when there is odd number at this place, there is iota with that term, and when there is even number at this place, iota is not present with these terms. Here in this case, it is given that n is odd, so it means that at this place there is an odd integer, so there should be iota with this term, not iota raised to power n. And when n is odd, then n minus 1 is an even integer, so there should not be term involving iota with this term. So to rearrange these terms, we can write iota n minus 1 equal to iota raised to power 2 into n minus 1 by 2. We know that iota square is minus 1, so it will be minus 1 raised to power n minus 1 by 2. So we will replace this term at place of this term. And also we can write iota raised to power n equal to iota into iota n minus 1, which can be rewritten as iota into iota square into n minus 1 by 2, which is equal to iota into, since iota square is equal to minus 1, so it will be minus 1 raised to power n minus 1 by 2. So we will replace this term in place of iota raised to power n, and we get this equation. You can see that it is same till this term, and we have replaced the value of iota raised to power n minus 1 and nc n minus 1, which we have calculated through this formula, and it is equal to n. Here we have replaced the value of iota raised to power n, which is this value, and NC n is equal to 1 by this formula, so here we have not mentioned it again. Now by equating real and imaginary parts, we can use these two equations to express cos n𝜽 and sin n𝜽 as finite sums of powers of trigonometric functions of theta when n is an odd positive integer. So this was the first application of De-Moivre's theorem.